Hello everyone, hope you are doing well and healthy. I will explain the effect of coastline orientation on a storm erosion using numerical modeling, taking example from Sylt Island. This work was carried out as part of the MODEX project, which has been funded by German Research Foundation. Sylt Island is located at the eastern part of North Sea. Here is a closer look. Right side is Wadden Sea, left side is North Sea. North Sea coast of Sylt Island has a convex shape extending about 35 km length. For numerical modeling, we use two model grid, apex grid, west grid. Apex grid covers central part of the coast, and we simulated morphodynamic within this grid. Purpose of west grid is to generate boundary posing for apex grid. We use data from 4 monitoring stations. H is tide gauge, B and L are wave buoy locations, LW is a wind station. We use two process-based numerical models, Delft3D and XBeach. This figure shows main processes within a single time step. We have initial bathymetry, boundary posing from waves and currents, and then sediment transport is calculated, and then bottom changes are calculated, and this is added to the initial bathymetry, and so on. Here is a comparison of some physical processes which are relevant for beach dune erosion. Short wave is computed in both models. Long wave is computed only in XBeach. Wave is computed in both frequency and directional domains in Delft3D, but only in directional domain in XBeach. Return flow is available only in XBeach. Avalanching processes are calculated in both models. Boundary forcing. Top panel shows water level information at this location. Middle panel shows wave characteristics at this location, and bottom panel shows wind information here. X-axis is time, Y-axis is parameter. We selected 3 events, P1, P2, P3. In P1, there are higher water levels and surges, wave height and wind speed. In P2 and P3, they are lower. Here are the characteristics of these 3 events. P1 lasted 7 days, P2 and P3 10 days. So these are the maximum water level of this event, and these are the characteristic of wave and wind at maximum water level. So P1 is extreme event, P2 is a weak event, P3 is a intermediate event. We simulated these 3 events in 2 series, cluster and isolation. In cluster, we simulated in sequence. In isolation, we use same initial bathymetry and pause with each event separately. For results, I will show you first wave dynamics and then morphodynamics. We analyze the wave spectral density. XBeach compute root mean square wave height. We converted that one into significant wave height using this relation. We estimated wave spectral density for the Jones-Upper spectrum using this relation. Here is a qualitative comparison of wave spectral density, P1, P2 and P3. The first panel shows wave height, x-axis is wave height, y-axis is time, red is from B and black line is wave from L. Other 3 panel shows spectral density. Those are the normalized value with respect to the highest spectral density in each event. So this is from Delft3D. So this is from XBeach using root mean square wave height, and the last one XBeach using significant wave height. Here we can see second panel and the third panel seem to agree, and here second panel and the last panel seem to agree, and here also second panel and the last panel seem to agree, and here we can see lower spectral density. Then we estimated the mean X spectra within each period, P1, P2, P3. X-axis is frequency, y-axis is spectral density. It should be noted that P1 has one order of higher spectral density compared with P2 and P3. So what are these lines? Red from B and black line is at L. So those are the measured information. And other three lines from model prediction. Yellow line from Delft3D, dash line from XBeach using root mean square wave height, and the blue line XBeach using significant wave height. In the extreme event, we see single peak spectrum at low frequency, and here we can see Delft3D and measured data agrees better. So yellow and black lines. In the weak events, we can see two peak spectrum and they are moving to higher frequencies, and here also we can see Delft3D and measured spectra agree better. No? Good. Then we analyze using some statistical parameters. Here you can see mu is relative difference. This is the standard deviation and root mean square. This is P1, P2 and P3. For example, in root mean square you can see Delft3D results have lower values. No? So that means the predicted waves from Delft3D agree better with the measured information compared with that of XBeach. Good. Then we go for morphodynamics. So here is the cross-shore evolution. We selected 6 cross-shore profiles from C1 to C6 from south to north, and here is in the cluster. X-axis is shore distance, y-axis is bed level. Yellow line is initial profile, thick lines are from Delft3D, dash lines are from XBeach. Color indicates different event. What we see here, thick lines are together and dash lines are together. That means after the first extreme event, there are lower changes in P2 and P3. Also we can see the changes from XBeach is higher than in Delft3D. From south to north, that means from C1 to C6, we can see this erosion area is decreasing. Similar figure for isolation. So here it is quite clear. In the first extreme event, there are strong changes in both models. No? Those are the red lines. Good. Then we analyze bed level and sediment volume change within this area from -5 depth to 5 meter elevation. So first 3 panel shows bed level change. X-axis is initial bed, y-axis is final bed. So those 2 dashed lines indicate 20% deviation from the no change situation. Blue is XBeach, red is Delft3D. Here we can see strong changes when you go for the dune area. So this is dune to level, mean high water and mean low water. In P2, there are very weak change, and in P3 we can see some changes. Lower 3 panel shows volume change. X-axis is different bed depth level ranges, and y-axis is volume change. Negative indicates erosion, positive indicate accretion. In this depth class we can see strong accretion. From there to dune area we can see blue bars are extending, meaning that XBeach resulted in higher erosion. Here we can see very weak changes, and in P3 we can see some changes which are higher than P2. Okay, similar figure for isolation. Here we can see based on the severity of each event, bed level changes and volume changes. In P2 we can now see some changes. In P3 we can see the maximum changes are within this 20% limit. Also with the volume change, we can see similar trend. In this class, higher accretion. When you go towards dune area, we can see XBeach resulted in higher erosion. Good. Here is the Alongshore variability of erosion sedimentation pattern within this area. Yellow line indicates coastline and grey lines are contours, and here wave and wind directions are given. With respect to this black line, shoreward is erosion, seaward is accretion. Blue is Delft3D, red is XBeach. Dashed lines indicate net changes along the coast. What we see here, the southern coast, higher erosion from XBeach, and even around apex we can see higher erosion. And in P2 event, we cannot see any changes. And in P3 event, we can see some changes. Here we can see Alongshore variability of erosion sedimentation pattern depending on the severity of each event. Now we can see some changes with P2 event, and we can see in the P3 event some larger changes compared to P2. Good. These are my conclusions. With default parameter settings, both models were able to present observed wave dynamics, and Delft3D had the highest agreement with the observed data. In extreme event P1, wave from northwest and wind from west approached the coast, and that resulted in the strong erosion at the southern coast than the northern coast. Of a convex-shape coastline, apex is more vulnerable to storm erosion. Ongoing work investigated storm erosion and recovery using calibrated parameter settings against measured beach dune topography. Thanks for your listening.